All right, today we're going to tackle one of the absolute cornerstones of computer science. We're going to build a hash map right from scratch.
So, let's kick things off with a problem that is really at the heart of so much modern software. Picture this. You've got this gigantic pile of data. We're talking millions, maybe even billions of items. How in the world do you find that one specific thing you need, like right now?
Well, the answer is the hash map. It's this incredibly clever data structure, right? It uses something called a hash function to basically create a super fast shortcut, a direct line from a key to its value. And this isn't some obscure academic thing. This is the secret sauce behind your phone's contact list, giant databases, you name it.
Okay, so how does it pull off this magic trick? What's the promise here that makes a hash map so special?
The big goal, the holy grail, is to do all the main things, accessing, inserting, or deleting an item in what we call O of 1, or constant time. Now, don't let the O notation scare you. It's just a fancy way of saying how fast something is. An O of 1, that means it's pretty much instant. It doesn't matter if your hash map has 10 items or 10 million. The time to find what you're looking for stays the same. That's the dream.
All right, let's get into the nuts and bolts. To really get how this works, we're going to use a super simple but really powerful analogy.
Just picture a huge row of empty boxes. You know, like a wall of mail slots or cubbies. In the programming world, we call these buckets. And this simple row of boxes, that's the entire foundation we're building on.
Okay, so how do you actually put something in one of these boxes? It's a four-step dance. First, you take your key, let's say it's the word cat, then you run that key through a special hash function. Think of it like a magic black box that spits out a number. Step 3, you take that number and it tells you exactly which bucket to go to. And finally, you just drop your key value pair right into that bucket. It's like having a perfect magical filing system.
Now here's a little bit of a pro tip, something really cool. How do you turn that big, random-looking hash number into a valid bucket number? You could use a math operation like modulo, but that can be kind of slow. So high-performance hash maps often do this nifty little trick with a bitwise AND operation, which you can see here. It's lightning fast, but it only works if your number of buckets is a power of 2. It's a classic example of a clever, low-level optimization that makes a real difference.
But, no system is perfect. There's a catch. What happens when our magic filing system messes up? What if it tells you to put 2 different items into the same exact box?
Yeah, that's called a collision. It's when 2 totally different keys, like cat and maybe dog, go through the hash function and bam, they get assigned the very same bucket. And trust me, this isn't a rare thing. It's going to happen. It's an inevitable part of the deal. So we have to have a plan for it.
So what's the plan? Well, the most popular and easiest to understand solution is something called separate chaining. The idea is brilliant in its simplicity. Instead of each bucket holding just one thing, we let it hold a little list of things. So if a second item maps to a bucket that's already full, no problem. We just tack it onto the end of the list in that bucket.
Okay, but wait a minute. This should send off some alarm bells. If we now have to search through a list inside a bucket, doesn't that completely destroy our whole promise of O1 instant access? I mean, are hash maps really that fast after all?
And that's the million-dollar question. The answer is, it depends. The speed of our hash map is now totally dependent on how long those little lists get. If a list gets super long, then yeah, finding something in there is no longer instant. It's slow.
This chart right here shows the 2 sides of the coin perfectly. On a good day, the average case, you have a good hash function. The lists stay super short, and everything feels like O of 1. It's lightning fast. But in the absolute worst-case scenario, what if every single key you insert collides into the same bucket? Well, then your fancy hash map just becomes one giant slow linked list, and your search time plummets to O of n, which means you have to check every single item. Ouch.
So the big engineering challenge is, how do we stop that nightmare scenario from happening? How can we be proactive and make sure those lists stay nice and short so our lookups stay fast? The trick is to keep an eye on a very important number called the load factor. It's super simple. It's just the number of items you've stored divided by the total number of buckets you have. Think of it as a percentage that tells you how full or crowded your hash map is getting.
And there's a kind of rule of thumb, a magic number if you will. For most hash maps, once that load factor creeps up to 0.75 or 75% full, an alarm goes off. It's a sign that things are getting too crowded, the lists are probably getting longer, and it's time to do something about it. And that something is called resizing. It's a big deal. What we do is create a brand new, much bigger array of buckets. Usually we just double the size. Then comes the hard part. We have to go through every single item in the old map, one by one, recalculate its hash for this new bigger space, and find its new home in the new array. It's like moving your entire apartment into a bigger house and reorganizing everything.
Now, let's be clear. This whole resizing process is slow. It's an O of n operation, meaning it takes time proportional to how many items you have. But, and this is the key, it happens really rarely, so that big cost gets spread out, or amortized, over all the thousands of super fast insertions you did before it. It's kind of like paying a small tax every once in a long while to make sure the roads are always clear. Because of this, we can still confidently say the average cost of an insertion is O of 1.
Okay, so let's bring this all home. Let's say you're in a technical interview and they ask you to design a hash map. What are the things they really want to hear? What are the gotchas you need to know about?
Well, they're going to test you on the pitfalls, the common mistakes. They want to see if you know about things like what happens if you use a key that can change, like a list, or what's the disaster scenario if you just forget to resize. They're looking for you to understand not just how it works, but how it can break.
And for sure, you need to be able to talk about the different ways to handle collisions. We focused on separate chaining, right? But there's another whole strategy called open addressing. With that one, if a bucket is full, you just look for the next available one. It can actually be faster because it's friendlier to your computer's memory cache. The downside? Deleting things becomes a real headache. Being able to weigh the pros and cons of these two shows you really get it.
So I'm going to leave you with this one last thought. It's a classic interview question, and it really gets to the core of this whole thing. Imagine you put an object into your hash map. It gets hashed, it's put in its bucket. But then you go and change the object, and that change alters its hash value. The question is, what happens now? Is that object lost forever? Can you ever find it again? Something to chew on.